All right, in this video, we're going to be proving what the interval of convergence is for the function e to the x. And I like this problem because it ties a lot of different ideas in. It ties in convergence, it ties in the ratio test, it ties in Taylor series, and it ties in also the interval of convergence. So we're going to get into the example now. The first step to solving this problem is we have to set up e to the x as a Taylor series. So the formula for the Taylor series, f of x is equal to sigma of n equals 0, the index starting from 0, of f to the n derivative centered at a. So you're going to evaluate all your derivatives at your center a, divided by n factorial multiplied by x minus a to the power of n. And we're going to do this on the function e to the x. So the first step to solving e to the x in the Taylor series format is we have to take a bunch of derivatives. We know that from Calc 1, the derivative of e to the x is always e to the x. So the nth derivative of e to the x is e to the x. And then I'm just going to pick any arbitrary center, let's call it a, and I'm going to plug in a. So when we evaluate it at a, it's going to be e to the a. And this is our formula for the nth derivative evaluated at our center a, which we're going to plug into this formula right here. So f of x is equal to the summation starting from n equals 0 to infinity of f to the nth derivative at a is e to the a over n factorial multiplied by x minus our center a to the power of n. So now we've represented e to the x as a Taylor series centered at a. And now we're going to use this to do our convergence test. Just to recap, e to the x is equal to the Taylor series of this. And when we want to find the convergence of a Taylor series, we use the ratio test. And what the ratio test says is that we have a limit, call it L, and it's equal to the limit as the index goes to infinity of the absolute value of an plus 1 divided by an. Now, this might look a little confusing. What is an in this case? Well, I'm just going to let an equal whatever's inside our sigma. So it's going to equal e to the a over n factorial multiplied by x minus a to the nth power. And I'm going to plug that into the formula here. We say that e to the x is convergent if this limit is less than 1. So this has to be less than 1. So when we plug everything in, we get the limit as n goes to infinity of an plus 1. Well, this is an, so anywhere we see an n, we just have to plug in n plus 1. So let's do that. We get e to the a over n plus 1 factorial multiplied by x minus a to the n plus 1 power now, divided by an, which is just this, e to the a, n factorial, x minus a to the n. Continuing, let's do some simplifying. The limit as n goes to infinity of, I'm going to flip this denominator into the numerator by taking the reciprocal of it. So it's going to look like this. E to the a, this is still the numerator part here, with n plus 1 everywhere, x minus a to the n plus 1 multiplied by the reciprocal of the denominator. So everything on the bottom goes to top, everything on top goes to bottom. So n factorial over e to the a multiplied by, well, now we have x minus a to the n in the denominator. Now, you usually know that you're doing the ratio test right when you start to see that a lot of stuff cancels out, which it does here. So the e to the a on top cancels the e to the a on bottom. The n factorial cancels the n plus 1 factorial. However, we still have n plus 1 on the denominator because n plus 1 factorial is equal to n plus 1 multiplied by n factorial. So when we put that on the denominators, the n factorial cancels this n factorial. We have n plus 1 on the bottom still. And then with the powers of n on the x minus a, We have n on top, n on bottom. We can cancel the n's here. However, we still have an x minus a to the power of 1 on top. When you have powers and they're adding together, you can split them up by multiplying. So this is really x minus a to the n multiplied by x minus a to the 1. So then it's just the limit of n goes to infinity of x minus a to the power of 1 divided by n plus 1. And this has to be less than 1 for the e to the x to be convergent. And then we just have to solve this inequality. So when we're considering the limit as a variable of the index n going to infinity, x is treated as a constant, and a is already a constant. So what we can do is we can pull this part in the absolute value outside of the limit because it's treated as a constant. So you pull this out, you get x minus a multiplied by the limit as n goes to infinity of the absolute value of 1 over n plus 1, which has to be less than 1. Just to recap, when we were doing the ratio test, we got to this inequality, and now we have to take the limit as n goes to infinity, and this all has to be less than 1. So we have n plus 1 on the denominator, and it's going to infinity, so denominator gets really big. That means the limit is going to go to 0. So we have 0 multiplied by x minus a, which is less than 1, which means that this is true for all values of x. No matter what value of x I put in here, I'm always going to be multiplying it by 0, and 0 is always less than 1. So this is true for all real numbers x. So what that means is that our interval of convergence, the limit of the absolute value of an plus 1 divided by an is always less than 1. So we can say minus infinity is less than x less than infinity is our interval of convergence. And then just one last note. Anytime you have the interval minus infinity to infinity as your interval of convergence, the radius of convergence, I'll call it RC, is just equal to infinity. And that's everything.